Hello everyone. So today we're going to talk about Markov chains. So this is an application of matrix multiplication. In order to talk about Markov chains, I just need to first define a couple of properties for specific square matrices. So the first definition is what is a Markov matrix. So a Markov matrix is a matrix where all entries are positive and such that if you sum up every entries in every column, so if you take the sum of the entries in any column, you always get 1. And if you look at our examples below, all the matrices, the 5 matrices below are Markov, because if you look at the column 1 plus 0, that's 1, 0 plus 1, that's 1, 0 plus 1, 1 plus 0, 0.4 plus 0.6, 0.3 plus 0.7, 0.9 plus 0.075 plus 0.025, 0.15 plus 0.8 plus 0.05, that's 1, 0.25 plus 0.25 plus 0.5, that's a 1, 0.5 plus 0.5, and 1 plus 1. So all of them, all the columns, and here this is really a column definition. If you sum them up, they all give you 1. So all those, and of course all the entries are positive, so we're not looking at matrices where the entries are potentially negative summing up to 1. I mean, there's a whole theory about those things too, but for us, all entries need to be positive and they need to sum up to 1. So those 5 matrices are example of Markov matrix. So whatever bullshit you're doing with Markov chain in any question, at some point you'll be dealing with a square matrix. If the entries are not positive, and if the entries in the column, if their sum is not 1, you're missing the point. So whatever you're doing, whatever you're studying, if it's a Markov chain question, make sure that this matrix is in this format. And then the other definition, which is a bit more strict, but restriction of special Markov matrices, is the notion of a regular. So what is a regular Markov matrix? Well, it's just a matrix that goes to the washroom at every 2 hours. It's a matrix, it's a Markov matrix such that if you look at M, or at one of its power, where k is a natural number, all the entries are strictly positive. So in other words, if you start with a Markov matrix and there's no zeros in it, it's automatically regular. But if there are some zeros in the matrix, you need to multiply that matrix by itself until you get rid of all the zeros. Or if it doesn't happen, if for some reason some zeros they stay in forever, then this matrix, this Markov matrix, is not going to be regular. So let's look at some examples again. So I2, well, let's do the trivial ones first. So if you look at A is obviously regular because all the entries are strictly positive. There's no zero. Same thing for B. So the matrix B here, all the entries, so there's no zeros here. So these two matrices right away are regular. So now the only one we don't really know is I2, S, or C. So there are some zeros in them. It does not mean that they're not regular. It means that you need to multiply them by themselves and see if the zeros go away. So for the first one, if we look at I2, of course, if you multiply I by itself, I is the identity matrix, you're going to get the identity matrix again. And in fact, if you multiply I2 by itself forever, you're going to get I2. So in other words, these evil zeros are going to stay in your matrix. So I2 is not a regular Markov matrix. What about S2? What about S, sorry? Well, if you compute S2, so let's multiply S by itself. So if you go S times S, remember here we're doing matrix multiplication. So the columns are falling on the rows as usual. So here you're going to get 0 times 0 plus 1. So you're going to get a 1. And then 0 plus 0, which is a 0. And then second column, 0 plus 0, which is 0, and then 1 plus 0, which is 1. And of course, you're getting the identity here. So if you try to multiply S squared by S and computing S cubed, so S squared times S will be the identity times S, which gives you the S matrix again. So here, this matrix S, when you're multiplying it by itself, will oscillate between two possible matrices. So Sn is going to be S if n is odd, like 1, 3, etc. Or it's going to be the identity matrix if n is even. In other words, you're not getting rid of the zeros for even powers or odd powers. So S is also not regular. What about C? Can we get rid of those zeros at some point? So again, here I already said that A is strictly positive, so it's regular, all the entries, same thing for B. So what about C? Well, if you multiply C by itself, so if you compute C squared, you're going to get 0.5 times 0.5 plus 0.5 plus 1, which is 0.75, and then 0.5 times 0.5. So remember, doing rows times columns. 0.5 times 0.5 plus 0, that's 0.25, and then 1 times 0.5 plus 0 times 1, that's 0.5, and then the same for the other one. So by the way, every time you're multiplying these Markov matrices, they stay Markov, so when you add up the coefficients, the entries in every single column, you're going to get 1 again. But anyway, so now you see there's no longer any zeros, so C is regular. So two important notions. So these notions are defined on matrices, square matrices, so notion of Markov. So entries are positive, where the columns, they sum up to 1. And regular is just, well, if there's no zeros, it's regular. If there's some zeros, if you multiply these matrices by themselves, if at some point the zeros go away, then it's regular. So just a heads up here for us in most applications that we're going to construct together. In my examples in this section or in the examples in WebWork, the matrices that you're going to be studying are going to be Markov matrices, which are also regular.